Welcome to myprojectbazaar.com. Our project title is Distributed Sensor Network on Chip for Performance Optimization of Soft-Error-Tolerant Multiprocessor System on Chip. Abstract. As transistor density continues to increase with the advent of nanotechnology, reliability issues raised by more frequently appeared soft errors are becoming even more critical to the next generation multiprocessor systems. In this paper, we present a systematic approach to address the soft error problem in multiprocessor system on chip with the consideration of system performance optimization. To guarantee the system correctness, a hardware-software collaborated approach is proposed to protect the processor from soft errors. Tiny hardware sensors are embedded in the processor cores to detect the soft errors, and the software-based rollback scheduling mechanisms are applied for error recovery. The protection cost on hardware duplication and software redundancy are effectively reduced. To optimize the system performance, a distributed control system is built on the top of the on-chip communication network and collaboratively manages the entire chip for application execution. With the cluster-based task migration techniques, an efficient runtime task mapping and rescheduling algorithm is proposed to further mitigate the overheads included by software protection and to minimize the total performance degradation. The distributed control strategy makes a system more adaptable and flexible to the development of next generation hardware and software with larger scales. Extensive performance evaluation using System C based cyclic accurate simulation on a set of real-world applications shows that our proposed approach has an average 49% of performance improvement and 79.6% of energy consumption reduction compared with the related state-of-the-art techniques. And hardware synthesis results shows that our proposed approach only introduces 2.9% of chip area overheads. Let us see the flow of our project. First, in our distributed sensor network on chip, we have to implement our NoC design, and then our NoC design have 4x4 mesh topology, and then we have to give the input data for source and destination transmission. Then we have assigning the source. All the informations and the data packets are stored in the memory called SRAM, that is static random access memory. Many types of RAMs are used for memory allocation, but we are using SRAM for increasing the speed of memory usage. And next thing, we have to estimate the router, that is our system have our NoC design have multiple sensors, routing informations, processing elements and routers. So we have to first estimate the router information, then our distributed control system is proposed, which is assign the schedule for all the source and destination pairs. Then that distributed control system assigning task for each node. If any soft error occurs, it identifies that soft error. Then we have to evaluate our process, which reduce the area overhead and adaptability is increased. Let us see the output of our project. First, open the Xilinx window which contains our coding. In that, we have to implement our coding in VHDL language. First, click on this. This file contains all our coding process. So in our project have two parts. First one is implementation and next one is simulation. When we click on the simulation radio button, it will process our output file. So click this simulation behavioral model. So it will generate our output window. This is our output window. these are all our used bit information, that is number of wires and input elements, output elements are there. So in our project contains some processing elements, routers, sensors and all. So for processing elements and routers we use gateway nodes. So this injection data is nothing but the input data, ejection output data is nothing but the output data, and P1 to this P39s are wires and these are gateways. So when we click on that, so first set our clock and reset. So give the value for a clock in clock, give the value for force clock. So first give 0, 1 and the period is 1000 nanoseconds. So first reset this a constant. First of all give 1 as process. When we click on this run icon it will start. So now start, then reset this is this as to 0. So all the information which is given in this that is 01010011 is passed to the these wires, that is P1 to P39, and that information, that is source information, is passed to that gateway node and the destination is getting the information. So now we have to enable this WR, that is write enabler as 0, which is used for pass the information to the routers. So now the information is passed to the destination via routers. For that case we also do one thing, that is we also enable this write enabler as 0. So we have to enable these are all as 0. So give 0 for all write enabler 0. So now click on this run icon, it will start the process. Now injected data is 01010011 and it will processed, that is the gateway node, here, that yeah, gateway node 2 is getting the information from that source node. So gateway 2 is act as a router element and it passed the information to the destination, which is shown here. Yeah, so our input data is passed here, so output is produced here. This is our simulation result. Let us see the implementation result of our project. Just close it, open this implementation. In that, this synthesis XST contains our implementation result. In that design summary, click on this synthesis report. It will show our number of flip-flops used and latency, delay and all. So here, so we use minimum period as 1.149 nanoseconds. So all the results are displayed here, and the number of LUT used. Are displayed here. So for our RTL diagram, click on this view RTL schematic. Okay, so add our main file, which is create our schematic file. This is our IC chip. When we click on any one of the process, our process is a huge process. When we click on this process, so just view, zoom it. So when we click on this process, our process output is shown here. So this is our output file. So each file contains many RAMs and flip-flops. So this is our output file which contains, this is for our single injection data. When we click on each this icon, it will produce our file. So this is our RTL diagram. Thank you for watching.